Hello. Unfortunately, there's no easy way to say this, so let's just dive in. Things aren't looking good. I know Dale said on Tuesday, we really shouldn't be peddling fear in this industry, but at the end of the day, when we look at the rise of memory safety vulnerabilities in the last 8, 9, 10 years, the numbers speak for themselves. They don't look good. And we're going to get into that as part of this talk, but I mean, with the exception of 2 years where we had some drops in this number of vulnerabilities in the memory safety side, we're seeing almost a very linear, if not in some cases, exponential growth in these memory safety vulnerabilities. And particularly as we look at ICS devices, OT devices, we're seeing more connectivity requests from asset owners. We're seeing requirements coming down to have updates available. Well, if you're going to update them, you're probably connecting them to a network somewhere. So this is a bad thing, and we've got to figure out a way to solve this. So what are memory safety vulnerabilities? They're bugs in software that lead to things like logic errors, where an attacker can change how the device is operating. They can lead to remote control of your device. That's really bad, right? If we've got manufacturing or SCADA systems, we don't want attackers controlling how much water goes out or how much chlorine goes in the water. But they can also lead to denial of service attacks. So in the IT space, that's maybe less interesting, but if you're denying service for a substation or for a water system, that's not good. So how do we know what vulnerabilities? We've heard a lot this week about SBOMs and vulnerability management and how do we prioritize? Well, these memory safety vulnerabilities, there's about 85, 86 of them, probably more. I mean, the CWEs change quite frequently, but there are things like buffer overflows, use after freeze, heap-based buffer overflows, out-of-bounds writes. There's a lot of them, and they're very important and impactful on devices. And okay, well, there's 85 of them out of hundreds, if not 1,000 plus CWEs. Why should I care? Well, according to MITRE, they're 5 of the top 10 most exploited CWEs for 2023. So we've got hundreds or 1,000 plus CWEs, but they're the majority of what's being exploited today. So that's not good. And they're really sticky. They're 5 of the 15 most stubborn CWEs over the last 4 years. So they're getting in devices, they're getting in software, they're sticking around for a while, and that's not good either. So they're very stubborn, they stick around, and well, we're doing a lot better, right? I mean, we have to be. 10 years ago, we weren't talking about secure software development lifecycles. We weren't doing scanning as much. But why are we seeing then that these memory safety vulnerabilities continue to be more and more every year? And part of the problem is these best practices, while great and we should continue to do them, as a security practitioner, I'm always going to say, let's do more security, let's do the best we can. But patching every vulnerability is costly, it takes time. It's disruptive to your developers, right? If you're a device owner, you want to implement the next device or the next feature in your device. You want to improve performance, you want to improve reliability. You don't want to be stuck patching vulnerabilities all the time. It's disruptive to that process. It's disruptive to your asset owners when they've got to take their systems down to do patches. And in a lot of cases in the OT and ICS space, patching is difficult. Everybody here knows that, but I have to say it, it's difficult. So that's not good. We've got to come up with a better approach. And then, one of the things that I've seen in my career in cybersecurity is that any process that we have that is driven by humans, that has a lot of human input, is prone to human error. We're not perfect, and that's just the way life is. We're never going to fix that. But everything in the secure software development lifecycle relies on humans. It's human code review, human configuration of your SaaS and DaaS tools. It's humans picking what software they're going to bring in. So as you look at your supply chain, did you pick the right dependency? In all those places, we can have human error, and that's what's starting to contribute to these memory safety vulnerabilities being in our devices. It's hard to write really secure code. We look at CISA and they say, let's write Rust code, let's do more Golang. Well, there's memory safety issues in those languages. Your dependencies can have unsafe code there too. So it's not this panacea that some people would like you to believe. And this is a shocking stat here. So I'm glad everybody else in the room is seated already. When I heard it, I wish I was seated. Your SaaS and DaaS scanning tools aren't finding all your bugs. Everybody knows that. But Some research by NC State University found that 97.5% of bugs identified in open source software, they looked at about 10 packages over 15 years. And over that 15-year period, only 2.5% of bugs that were ever identified in those software packages were even identified as possible bugs in code scanning tools. That's terrifying, right? Hey, we're finding buffer overflows, we're finding issues, we're patching them, and that's great, let's keep doing that. But the unknown world is way scarier and way more prevalent than I would have thought prior to this research coming out last year, 2 years ago. So that's also not great. And then, we've heard a lot this week about software bill of materials. It's coming, it's requirements from the executive orders. We're seeing asset owners ask for them. We're seeing OEMs struggle to produce them. But one of the companies that we've talked to about their problems with SBOMs, they went from probably a single-digit number of vulnerabilities they were tracking for a product to generating an SBOM, and now they have over 1,000 vulnerabilities to track and triage and remediate for one product. And they're a huge company. I'm not going to name them, but that's crazy. How do we deal with that? And if you look at Schneider Electric's talk in their demo room on Monday, they talked about this, I think, in their presentation. There's a ton of false positives in that as well. So now we're spending a bunch of extra cycles triaging bugs that don't exist in software. Well, that's not great either. And so that's not where we need to be. That's not how we get more secure devices. Now, we should still do software bill of materials, right? We need to understand what's in our supply chain. We need to understand the vulnerabilities that actually exist there. But there's still a lot of work to be done in getting those software bill of materials to be accurate and provide you good data that you can act on. Although I will say there are companies that are doing good jobs with that, but there's still a lot of work to be done. So let's talk about things you can do today, right? Control flow integrity, you can turn that on in your compiler if that is supported for your environment. But a lot of OT devices, ICS devices, don't have a spare 25% processor overhead to turn on control flow integrity. And that's assuming CFI doesn't break your software. Unfortunately, those implementations today aren't just 100% applicable out of the box. That's why you don't see that turned on by default in the compiler. It can create problems. So while you could turn that on, you're likely going to break your software. There was a cool talk earlier this week on this stage about ARM's research with the Morello chip and Cherry. That's really cool, but we can't do that today, right? If a device manufacturer wants to go deploy on Morello, there's not a chip they can buy and deploy, much less get that into their supply chain. We're years out from that. And if we look at CISA's Secure by Design, everybody in the room, who wants to go rewrite all their code in Rust today? Yeah, exactly. I have one hand, that's great. We actually have done that. We did that for one of our product offerings because we have code that runs on end user devices. It took time, it's hard. Our development time has slowed down a little bit because we're C++ programmers, we're not Rust programmers. So there's additional challenges to developing that and maintaining that. So this is all good, but we're ICS, we're different. Right? I've been in industry, in the cyber industry, doing vulnerability research for a long time. Every industry I talk to is different. We're all unique, and yet everyone has the same problems. In fact, I heard this from somebody yesterday. We have different security standards. We have different development cycles. Everything's different. We don't have this problem. Well, what I did was I went and looked at the CVE data for the last 8 years or so for 5 of the top 10 ICS device manufacturers. And I said, let's dig into that data. Is ICS different? Is SCADA different? Is OT different? And it's different, but it's worse. It's not good. Microsoft and Google will tell you 40 to 70% of their bugs, depending on product, are memory safety related. In the ICS space, it's 70%, or 72%, sorry, are memory safety related. So we're worse. We're worse than IT. We got to fix this. But potentially the most alarming stat on this slide here is that for every vulnerability out there, the average number of CPEs, the average number of products and versions that are affected is 10. So that tells me one of two things. Either software is getting vulnerabilities and it's lasting for a long time, so version by version, that vulnerability is present and ends up affecting a lot of versions, or you have a lot of shared code across all your products. Well, that's not great because now if an adversary finds a bug, it's applicable to a lot of devices in your customer ecosystem. So your asset owners can't say, well, I don't deploy that SKU, so it doesn't affect me. If it's shared across everything in your portfolio, now everything's vulnerable and your vendors, your asset owners are gonna be vulnerable too. And 70% of these bugs are higher critical, so you don't even get the free pass to say most of my bugs are low, I'll get to them eventually, which, come on, let's be honest, nobody's patching low vulnerabilities. We got enough high and critical to deal with. So that's not great either. And 70% of this was a shocking stat to me in the ICS space. 70% of them got scored as remotely accessible. Wow. That's not good because we're going to have more remote connected devices. We're putting things connected more and more. This means that we have these high and critical vulnerabilities that are accessible to attackers. And they may not be internet accessible, but an attacker can come in, they can move laterally through your network. So we don't want to do that. So, okay, surely these bugs don't live that long, right? Oh, I'm sorry. These numbers are even worse. Urgent 11 existed for 13 years in VxWorks. 13 years. And a lot of security researchers have looked at VxWorks in that 13-year period. And that's not good. Ripple 20, the next batch of big vulnerabilities in RTOS, existed for 12 years. I mean, okay, it's better by 1 year, but that's not great either. And so, let's look at some academic studies. One study found that for memory safety bugs, the average lifetime is 2 years. Other research is suggesting the average is 5 years. So these bugs are landing in code, they're not getting found, they're not getting fixed, and sometimes the fixes are accidental. Someone didn't mean to fix a security vulnerability, they just changed some code for a feature or for an optimization and a bug went away. So that's kind of funny too, is that some of these bugs get fixed by accidental fixes. But here's the scary thing. ICS vendors average 140 days to release a patch. For IT systems, for browsers, for complex software in your enterprise, that number is way down. It's hard to tell what that number is for non-ICS, but Trend Micro did some studies with ICS vendors and found 140 days from them finding out a bug to having a patch. That doesn't mean that the asset owners got a patch or it got deployed. So that's an eternity. I mean, really, as an asset owner, hopefully that disclosure is private. But what happens when it's a public disclosure? Someone's on stage at Black Hat or DEF CON and there's 0 day. What do you do as an asset owner, right? All you can do is ask your vendors, ask your suppliers to be better, do more security. So that's a pretty bleak past, right? And as Dale talked about on Tuesday, we don't want to be selling fear. We want people to believe that there's a path forward. So thankfully there's a bright future ahead. And we're going to talk about how people today can deploy existing technologies to help reduce this problem space in a very meaningful way. So the solution here is RASP. Now, I know in a lot of people's minds, RASP is not a good term. It doesn't apply to ICS. And largely that's because people are thinking about RASP in terms of older RASP technologies. It's basically a web app firewall, and we'll talk about that in a second. But RASP is runtime application self-protection. So the idea is, as a device manufacturer, you don't control where your asset owners deploy your assets. You can't control the security protections that are placed on the network. You can't control what they're connected to. And I'm sure everyone in here has some horror stories of walking into a manufacturing plant or a substation and going, wait a minute, why is that in the DMZ? That doesn't belong there. That's got to be behind our security infrastructure, but for some reason it's not. So we want to be able to help. RASP allows you to deploy security protections at the last possible place you can protect against attacks. And that's really important. As device manufacturers, you can help your asset owners deploy better solutions, more secure solutions, regardless of what mistakes they make in their deployment, or regardless of what mistakes the integrators make. And there's really three kind of categories. I'll break them down into three. Some people might say there's 2 or maybe more. But really it's web application RASP. That's pretty common in the IT space, but there are OT solutions for that as well. And then there's passive and active varieties, and we'll talk about those in a second. So what's really cool is, as CISA first came out with Secure by Design, they said no other technology can solve memory safety except for writing in memory safe languages. And there was a lot of pushback, and I think rightly so. They've got a really hard job of telling people to do something today that they can't do today. But they came out with a second rev of their Secure by Design document and said, okay, we get it. We have to give you a little bit of wiggle room. If you have to, turn on compiler options, use some other tooling to help give you that memory safety in your C++ code while you figure out your roadmap to getting to memory safe languages. So it is recommended there. It's also recommended by CISA in their secure supply chain documentation. So we'll spend a little bit of time on web app RASP, but that's not really my area of expertise. I'm more on the compiled side. But a talk on RASP helping your devices wouldn't be complete without it. So the really cool thing about web app RASP is they integrate with your web frameworks. So some SCADA devices, although a lot of them aren't running web apps, we're seeing more and more interconnected, REST APIs on devices for, sending sensor data or querying for sensor data. Kind of this modernization in some of the embedded devices. And so what's different between RASP and your typical WAF is that the RASP is going to have knowledge about the actual application itself. And so it's going to be looking for things like SQL injection, cross-site scripting, command injection bugs. So the talk before was talking about using Journ to find those command injection bugs. But what if we can look and get that protection on the web app side and not just on the compiled side? So that's where kind of web app RASP can really help you. And then we've got active RASP. So active RASP, the distinction I'm going to make here is that it's built into the firmware image, but it's taking an active role in the security of the device. So you can integrate it at source time, at build time. There's binary-based RASP solutions that just take a post-build object and can integrate the RASP there. But what's interesting about the active side is that it's executing in line with your image. So that might be function hooks, it might be agents installed on the system, really just depends on the architecture of that solution. And you can do a lot of really cool things with active RASP. But you get increased protection at a cost of performance overhead. So what that overhead is going to depend on what you're doing in the device itself, but you do have some performance overhead there. But there's two really cool companies that are doing that today. Red Balloon Security has their Symbiote product, and it's an OS-agnostic firmware security tool. So it can take your binary, add in the Symbiote technology, and then they're kind of executing in empty space of your firmware, and they can then give you continuous runtime monitoring and intrusion detection. And so they can look at in-device memory, they can look for new kernel tasks, they can look for new processes launching, they can do a lot in that space. They can do behavioral monitoring, so if the device starts doing something it's not supposed to do, they can send up a signal and say, hey, something's gone wrong, or take a corrective action. And then you've got Sternum IoT. They have an on-device IDS IPS, and that's integrated at build time, and then it leverages binary instrumentation to deploy verification checks across their firmware. So in the picture here, this is from their website, but they're talking about doing a stack frame verification. So before you return from code, let's make sure that the stack frame is correct before we allow that return to happen. And then they can do some behavioral analysis as well to detect post-exploitation activity. And then finally, we're going to talk about passive RASP. Then we're going to actually go into a case study of why we should care about RASP. So with passive RASP technologies, you have no code executing alongside your existing firmware, and it only alters the behavior of the device under attack. So your state diagrams are pretty much the same, but when the device comes under attack, that's when you're going to get this protection. And so that's where RunSafe Security's code product comes in. It gets compiled at build time. And what we do is that when the device loads, we randomize where the code is in memory inside of the already allocated space. So instead of looking for vulnerabilities everywhere, we're taking away the primitives that attackers need to carry out their ROP and JOP type attacks against these embedded devices. But we are OS and processor architecture dependent. So unlike the Red Balloon solution or the Sternum solution that's a little bit more OS agnostic, we do have to care about the operating system and the processor. So let's dive into a case study. This is a real-world vulnerability, CV 2020-8597, and it's a vulnerability in the point-to-point protocol daemon. So I'm not an expert in this daemon, but basically it allows two devices to kind of talk together, and you can act as a modem and get access to the internet or other network ports. And there's really only 6 versions or 7 versions vulnerable, 2.4.2 to 2.4.8. But that product is so stable that this bug is 17 years old. It got introduced 17 years before it was identified. So we talked about the average is 2 years, maybe 5 years. This was 17 years. It's a CVSS v3 scored as a 9.8. It's remote, it's pre-authentication, so that's pretty crazy. And it's a classic buffer overflow. So if we go to the database, NVD, and we look up this vulnerability, what devices are vulnerable? Well, it only lists 4 CPEs. The point-to-point protocol project itself, Wago firmware, Debian, and Ubuntu Linux. And a lot of people in this room are going, whew, awesome, I'm not vulnerable, right? Well, oops, if you go to the ICS cert and look up the exact same vulnerability, there's 19 plus vendors that are affected. Oh, well, that's a very different story, right? Siemens is on there, Wind River Linux, Sierra Wireless, TP-Link. The list goes on, Cisco, Netgear, Yocto. It's prevalent, it's everywhere, and that's really scary. If you were just using the NVD data, you might think, I'm not vulnerable to this. But yet, here we are, and you actually could very well be. This probably isn't even an exhaustive list. So let's dive into the vulnerability. I mentioned it's a pre-auth vulnerability. So you've got this EAP protocol for doing authentication. A malicious attacker can send this packet to the client or the server listening, because it's a bidirectional protocol. And you can send this malicious packet, and inside the point-to-point protocol daemon, it's going to hit this EAP input function. And that function tries to do some input validation to make sure it's valid. But the check that it does is bad. And so this EAP packet can have a host name specified. That's optional. You don't need to specify it, but you can provide it. And they calculate the length of that buffer and check to see if the destination buffer's got enough size to hold it, but that check is wrong and you get a buffer overflow. So then that packet gets validated successfully, and then you end up in the EAP request function that's actually going to process this request for authentication. And this is where you have the bcopy function, that R hostname, that optional hostname that comes in. This is where the buffer overflow happens, because that IMP object isn't actually guaranteed to be large enough to hold that. So it's a super trivial buffer overflow to exploit. And in fact, one of the devices that we looked at for this vulnerability, for whatever reason, this protocol daemon wasn't compiled with FPIC, so it's not position independent, so you don't even get ASLR here. So exploitation of this was so trivial, it was kind of laughable and took me back to the old days of exploitation. So then, as an exploit, we're going to then pivot from our overflow over to a ROP gadget in TDB chainlock read, which sets up the stack, sets up a few registers, and then returns to this device script function. And that's where we're going to execute our payload on the device. And at that point, the adversary has control of the device. For the one device that we did actually prove this out end-to-end with, everything was running as root. So that's not great. Please don't do that. We have user devices in Linux for a reason. Let's use those user accounts. So I said we're going to talk about where the RASP solutions can provide mitigations. So the first place that Sternum can provide a mitigation is at that buffer overflow. They're going to get to that return address for that EAP request function and see that the buffer allocation, or sorry, I'm one slide ahead of myself. They're going to actually see that copy and say, hey, that copy is not a valid copy, and stop the buffer overflow from happening, error out, and the adversary is not going to be able to gain control of the device. The second place they can provide that validation if you don't have the buffer overflow checking on is to actually look at that input validation and validate that the stack frame is correct. And in this case, the stack frame is not going to be correct, so you won't be able to take control there either. And then on the passive side, RunSafe's RASP solution is going to impact us when we return to that stack pivot. So the attacker has put in their address that they want to go execute after the buffer overflow, and the memory's been randomized, so that gadget's not there anymore. So the exploit fails. And so that's where that payload's never going to execute. You don't have to worry about behavioral analysis because you're just going to be not executing anymore. And then past that, let's say for some reason you don't have those other solutions turned on the Sternum case, Sternum and Red Balloon will be able to do behavioral detection and see that a payload got executed that wasn't normally executed, right? So, hey, we're doing an EAP packet. Why are we running a call on the system function to add a new user to the device, or send out a new network port and do a remote shell connection that way? So they can look for things like new kernel tasks, new processes, unexpected file accesses. So there's a lot of great places for RASP today to help with these memory safety problems. So my call to action for device owners in the room is let's kill off memory safety vulnerabilities by deploying RASP today. We don't have to wait for 5 years for new hardware to come out. We don't have to work on porting our code to Rust. Although if you want to do those things, great, please do that. But we need a solution today. So let's do that. Asset owners, ask your device manufacturers why they're not deploying RASP in their devices. We really need to get this down, and killing off entire classes of vulnerabilities is really the only way I see that we're going to have a sustainable path forward. So thank you.